So all this kind of relatively mathematical and jargon discussion has some relatively practical implications for how to specify your regression model. And it's my experience in this course that after teaching all kinds of complicated tests and models and specifications, the main questions that students are left with at the end of the course is, yeah, okay, but which variables should I now put in the regression and which should I not? And so it's after that I introduce this class as well. If the aim of your analysis is some kind of causal inference, and this is in most social science applications the case, then the main thing to think about is what are confounders. And keep in mind, as we started with this lecture, that confounders is a causal concept. We're talking about causal relationship, not correlations. Yeah, so in all these conditions, there are all kinds of correlations, whether C causes Y or Y causes T, whether X causes T, like it doesn't matter what the directions are of these arrows. In all these cases, you get correlations. The question is what is happening causally, and that is primarily a theoretical question. Only in some research design can you really establish empirically, for example, experiments, which we'll mention briefly. So when do we control? The first is very straightforward. If there is a confounding variable, a variable that affects both the treatment and the outcome, you must control for this variable. This is essential to establish whether there really is a relationship between the treatment and the outcome. Yeah, so if there's some third factor, some third variable that impacts on both, we do control. Imagine there's a variable that is influenced by the outcome variable. I have a college degree, I obtain a higher salary, I use this salary to drive a faster car. If I'm going to control for the speed of my car, I have a problem, right? Because I'm going to underestimate the impact on my salary, because I'm taking into account I control for the speed of the car. Pretty silly example, but there you go. Then you really cannot control for this variable in the model. So if the causal diagram looks like this, treatment causes Y, Y causes X, you cannot include X in your model. And now this sounds like a very silly example that one of course wouldn't do, but I will show you in a couple of slides that people often do this. And so this is actually a major problem. The story gets a little bit more complicated if the treatment causes some third variable X, which in turn causes the outcome variable Y. If you want to know the impact of the treatment on the outcome, you should not control for X, because you're going to leave out a particular amount of the impact, namely what goes through X. So you end up with an underestimate. Imagine we have a scholarship scheme, and the scholarship scheme is to help students get a college degree. And a scholarship might then help their future salary, primarily because these students obtain a college degree. If I control for a college degree in my estimation of the relationship between having a scholarship or not and future salary, I heavily underestimate the impact, because the whole point of the scholarship was to help these students get a college degree, which then should help their income. So definitely do not control for the mechanism. However, in some cases, you might actually be, for some theoretical reason, interested in this direct effect. So aside from a scholarship helping people to get a college degree, which then helps their future career, it might also be the case that having a scholarship on your CV signals certain skills and therefore helps your future salary. So your employer will have seen that you obtained a scholarship, and this might actually help your career. So there might be a direct effect, regardless of getting the college degree, from having a scholarship on future salary. And if your research is particularly interested in that direct effect for some reason, then you should control for the mechanism to see what the direct effect is outside of getting a college degree. But that's a very specific kind of circumstance, but it might fit with your research question. Now, another very common scenario is that you have some variable that affects the outcome, but you have no particular reason to believe that it affects the treatment. In this case, you generally want to keep the model a bit simple, and you probably do not want to include it in the model. There's no good reason to do it. And we do have a problem of overcomplicating our regression models in general. That said, it can lead to efficiency, it can lead to a model that fits the data a little bit better, and therefore leads to smaller standard errors. So it can improve the model fit, and it can improve therefore the quality of your estimations. So that might be a motivation to keep them in. What I see very often in empirical papers is that the inclusion of control variables is motivated by arguing how this particular control variable affects the outcome variable. That I would always send back in my review to tell the right author that they need to revise this, but needs to argue why the control variable affects both the treatment and the outcome variable. If it only affects the outcome variable, it's not a proper control. It might increase the efficiency, it might increase the model fit a little bit. It's not what we call a control variable. A control variable is those variables that are potential confounders, that affect both the treatment and the outcome, and that are for that reason important to take into account. So when you, in your empirical work, include control variables, and you write a little section to explain why these are the relevant control variables, please do explain why they affect both the treatment and the outcome variable, not just one of the two. So all of this also suggests that one particular practice that is actually very common is highly problematic. So one thing that you often see is that people come up with different alternative theories as to what would explain the outcome variable. They come up with variables that capture each of these different theories. They put all these different variables in one regression model, and they look at which are significant and which are not. And then they conclude that those theories that have significant coefficients are the better explanations, and those that are insignificant, that those theories we can reject. This is highly problematic because it does not focus the research sufficiently. What all the previous slides tell you is that once you know what the treatment is, you can carefully consider which X variables might affect both the treatment and the outcome variables, and so need to be included, and which variables might be mechanisms through which the treatment impacts Y, or might be effects of Y changing and so forth, and you really cannot include those into the regression. If those different theories that you have are purely independent of each other, they're not related to each other, so they all independently, all these different X variables independently impact on Y, but they do not impact on each other, then okay, probably this approach might work. I would still be a little bit careful concluding that a theory doesn't hold when you have an insignificant effect, but that's a little bit of an aside. But in terms of model specification, you're okay. But very often this is not the case. Very often these other theories also impact on each other. So I gave an example where I might look at turnout, participation in elections, and I might say that some people say that people that are very interested in politics are more likely to vote. Others might say that people that have a lot of knowledge might see the relevance and more likely to vote. Other people might say that those that are socioeconomically are better off are more likely to vote. Now imagine that I capture then variables for each of those. I measure political interest, I measure political knowledge, I look at some social demographics like income and social class and so forth, and I put them all in one regression model, and I try to regress this on turnout on all these variables, and I see which variables are significant or not. Then really a major problem arises. These socioeconomic variables will also impact on interest, and interest will impact on political knowledge. So while when I want to assess the impact of political knowledge, it is important to control for interest and social demographics, the reverse doesn't hold. When I want to assess the impact of interest, I definitely should not be controlling for political knowledge, because it's a mechanism through which political interest matters. And if I want to know the impact of political interest, I should be controlling for social demographics, but not for political knowledge. But when I assess the impact of social demographics, I should not be controlling for either political interest or political knowledge, because these are mechanisms through which social class impacts on participation. So for the test of the political knowledge argument, we had the correct specification, but for the test of the other two theories, we had the wrong specification. So this idea that you can just find variables for a set of competing theories, put them all in one regression, and then see which ones are significant, what some people call the kitchen sink approach or the garbage can approach, it does not work, right? Because for some theories, you have the correct specification, for other theories, you have the wrong specification. To determine how to specify a regression model, it is always essential that you know which of the independent variables is your treatment. Because if you know which one is your treatment, you can argue what are potential confounders and which control variables need to be added. If you do not know which of your independent variables is your treatment effect, there is no way of deciding what variables to include or exclude from your regression, other than statistical, looking at correlations, but not a causal theoretical reason. You cannot look at confounders. You cannot talk about the idea of a confounder if you don't know which of your independent variables is your treatment. So you need to focus. Regression is about establishing the relationship between one independent and one dependent variable, and everything else is there to control, and you need to argue why they need to be there. Now, to do this, to do all this reasoning, to look at for each variable whether it's relevant or not, it is always a good idea to start off with a causal diagram. Take all the variables you might potentially want to include or that are in your survey, and draw a diagram like this that has all the arrows of potential variables, how they are potentially linked. And that will help you then to decide when you select one of those as your treatment, what control variables to add, what definitely not to include, how they are related. So start your research by making a diagram based on theory, based on the literature, based on what you know, what might be causing what. So another way of talking about this kitchen sink approach is to think about Y-centered or X-centered research. So in John Garing's work on political methodology, he makes this distinction between research that is Y-centered, where we have a particular outcome and we try to come up with an explanation of this outcome, and X-centered research, where we have a particular cause of this outcome and we try to establish what the effect is of this cause on the outcome. And so to do proper regression analysis, to do proper modeling and selection of your variables, you basically need to do X-centered research. You need to be aiming at assessing the impact of a particular treatment on the outcome. If you do Y-centered research and try to come up with all causes, you very quickly end up in a difficult modeling situation. For example, in a case study research, this might be more reasonable. A particular thing happens and you interview people and you read documentation and so forth to try to assess what might be a potential cause of this outcome. And it might be more Y-centered and it might make a lot of sense. But in quantitative analysis, you need to be careful. Of course, we can assess how different theories work relative to each other, but it's a careful modeling challenge. It is not simply a matter of throwing all possible explanations into regression and see what happens. So be careful with Y-centered research designs in quantitative methods. So we have discussed how we can identify what is a confounder, at least theoretically. But what can we do when we have some control variables, we have some confounders, and we want to get closer to estimating an average treatment effect? So we want to address this problem. There's a number of methods available. So the first and the ideal sort of method is the experiment. So in an experimental design, we can address most of these concerns about confounders. But then there are some other steps available, like blocking, matching, and multiple regression. Now we have talked about random selection. So when we do statistical inference, we do statistical testing to assess whether our estimates for a particular sample also hold for the wider population. And this is called statistical inference. To make a statistical inference, we need a random sample, or we need at least to know the probabilities related for each individual to be in the sample. So if it's not a random sample, we need to know how it was not random and have an estimate so we can assess this probability. And if we have this random this random selection, we can draw these statistical inferences. But since random selection does not impact on getting the treatment or not, this has nothing to do with causal inference. This only has to do with statistical inference. The experimental design revolves around random assignment. By random assignment, we mean that we control the treatment. We decide who gets the treatment and who does not. So, for example, in a medical experiment, we can imagine that we have a particular illness and we give half the patients a particular drug, T equals 1, and the other half we give a placebo, or we do not give a drug, T equals 0. So in that case, we have randomly decided who does and who does not get the drug, and so we have random assignment. Random assignment means that it is impossible for any third factor to have impacted on the treatment. Right? They will only have impact. They can impact on the outcome. There might be all kinds of reasons why some people are sicker than other people, but they will not have impacted on the treatment. They do not determine whether somebody gets a drug or not, because it's random. And if it's random, there is no external factor, and if there's no external factor, there are no confounders, right? Because the definition of a confounder said this variable should change the probability of getting the treatment. And so if it doesn't, then it's not a confounder. So if you can purely randomly assign the treatment, there can be no confounders, and therefore the whole problem that we have discussed so far disappears. So this is really the ideal way to deal with confounding factors. Sometimes in experimental designs, we also explicitly take control variables into account. When we, for example, already know that there is a strong gender effect, and we know that impacts will be very different for men and women, then maybe we can randomly select a group of women to get the treatment and randomly select a group of men to get the treatment, but make sure that those two groups are of equal size. This will help avoiding that that the gender can be an impact in our study. Yeah, so we can add additional controls when we already know that there are particular variables we should be really worried about as potential confounders, and even in experimental design we sometimes explicitly control by making sure that we have equal sizes in each group, each category. And this is called blocking. And the final way in which we can address control variables, and the one of course that we apply most often in applied work, is multiple regression. So we can add potential control variables, potential confounders as control variables to the regression. We simply add them to the equation and then look at the effect of the treatment on the outcome, holding all the other variables constant in a way. So multiple regression is a way of addressing potential bias that you would have had in simple regression.